Hello students, Jai Hind. I hope you all are in very high spirits and you are staying fit and healthy. So continuing with the previous topics, today we will extend the things which we have studied in the previous lecture. We have discussed about resistance, the factors on which the resistance of a conductor depends. We have discussed about resistivity, conductivity, conductance. Here I must state that resistance offered by a conductor depends upon the temperature, the dimensions and the physical conditions like temperature, isn't it? While on the other hand, the resistivity, which is the characteristic of the material of a substance, it only and only depends upon the temperature and nature of material of the conductor. It do not depend on the dimensions of the conductor. So students, what I mean to say is that if a conductor is given and if it is stressed or it is compressed to some new dimensions, then the resistivity will always remain same, or a given conductor is cut into pieces. So each piece, each part of the given wire will have the same resistivity as that of the original wire. What I mean to say is that resistivity is independent of the dimensions of the conductor. Right students? So today we will discuss these two very important concepts. Effect of temperature on the resistivity, how the resistivity or the resistance of a conductor changes with the increase or decrease in the temperature. And next we will discuss about temperature coefficient as well. These two are related topics. So in order to understand this, first and foremost, we need to derive this particular relationship. The resistivity of the material of a conductor, it's given by M divided by N E square tau. This is, student, a very important relationship. Actually, while deriving this expression, we will also mathematically verify Ohm's law, right? So rho stands for the resistivity, N is the mass of an electron, E is the electronic charge, which is 1.6 into 10 to minus 19 coulomb. N, students, remember, it is the number density of electrons, that is total number of electrons present in the substance per unit its volume. So its SI unit is meter cube, per meter cube. Tau, you are aware, is the average relaxation time. Relaxation time is the time that has elapsed between two successive collisions. So student, this is a very important article from board examination point of view as well. In order to theoretically conclude that how the resistivity depends on temperature, you need to first prove it mathematically, right? So in order to verify this, we'll make use of the expressions which we have earlier proved. So, as we know, the relationship between current and the drift velocity. Current is given by NEAVD. We all are aware of it. N is the number density of electrons, that is the number of electrons per unit volume. A is the cross-sectional area of the conductor. VD, students, remember, it's the drift velocity of the electrons, right? It is the velocity acquired by the electrons under the influence of the external field in addition to their random motion. Also, we are aware VD, it's given by, in magnitude, it's given by E tau divided by M. Tau is the relaxation time, average relaxation time. E is the strength of the electric field. And in magnitude, actually it's negative of this. Negative sign will suggest that electrons drift in a direction opposite to that of the applied electric field, right? We have proved these two relationships already. So now what to do is, let's make use of these two relations. So from 1 and 2, what we get is, from 1 and 2, we get I is equal to NEA. In place of VD, we can write E capital E tau by M. Right? Okay. Now, let's make use of another very important relationship. You are aware, electric field is negative of the potential gradient. So, electric field in magnitude is potential difference divided by the length of the conductor. V is the potential difference applied across the ends of the conductor. L is the length of the conductor under conservation, right? So we are aware of this also. So let's represent E in terms of the potential difference. So what you get is I, it would be equal to N E square A. In place of E, we can write V tau divided by M L. Is it okay, students? So, what to do is, it may be rearranged in this manner as well. V is equal to M L divided by N E square A tau. Just cross multiply and simply try to rearrange the terms. Simply try to rearrange the terms. So what you get is, and over here I. Now look, just concentrate on this obtained expression. V is the potential difference, I is the current flowing through the conductor. Now concentrate on the term inside the bracket. M is the mass of the electron, which is 9.1 into 10 to the minus 31 kg, which will be constant. Length area for a given conductor, its dimensions will remain same, it will be constant. E is the electronic charge, as I told you, it's 1.6 into 10 to the minus 19 coulomb. N is the number density of electrons, which for a given material would remain same, it won't change, right? Tau, students, it is the relaxation time, it's average relaxation time, and it depends on temperature obviously, right? So, in case temperature remains constant, then tau will also remain constant. So, what I mean to say is that physical conditions remaining same, the entire term inside the bracket would be constant. Therefore, physical conditions like temperature remaining constant, what you get is this entire term will become constant, this entire term will become constant. So we can write V is equal to some constant multiplied by current, right? So what you get is, we can write it as V is directly proportional to I. This is actually Ohm's law, which we have mathematically verified. So what's the statement of Ohm's law, students? Physical conditions like temperature, mechanical strain, if these quantities remain constant, then the current flowing through a conductor is directly proportional to the potential difference applied across its ends. That is, V is proportional to I. So this is what we have mathematically proved. So this is the mathematical verification of Ohm's law, right? But anyway, in this article, we are supposed to prove this particular expression. So there is one more step left and we can easily arrive at this result, right? So we can represent, here we can represent R in terms of rho as well. So we are aware this constant is known as the resistance. This constant is known as resistance. So put this as equation number 3. Also, from Ohm's law we are aware V is equal to IR. Put this as equation 4. R is constant. It is the constant of proportionality for a given physical conditions of temperature and mechanical strain. So comparing from 3 and 4, what you get is, compare these two. So this constant is resistance. So R is equal to ML divided by N E square A tau. This is the expression for the resistance in terms of the average relaxation time. In terms of the average relaxation time. So this is again a very, very important expression, students. You need to remember this. Now we are aware resistance of a conductor is directly proportional to its length and inversely proportional to its cross-sectional area, isn't it? So R can be written as rho L by L. Rho is the resistivity. Rho is the resistivity. So it is M L by N E square A tau. So what we get is rho is equal to M divided by N E square tau. This is a very, very important expression, and the derivation of this article is very expected in the board examinations, right? So the resistivity, which is also known as the specific resistance of a conductor, is given by m over n e square tau. So this is the mathematical formula relating the resistivity and the average relaxation time. Now before proceeding, we need to discuss it theoretically. We need to interpret it correctly, right? So let's consider the cases. So first one, rho is inversely proportional to n. Physical conditions remaining constant, right? So what I mean is, n, students, remember, it is the number density of charge carriers, which are the free electrons. So in those substances like conductors which are having large electron density, n value is very large. So in conductors the resistivity is very low. So those substances having large value of n will possess small value of resistivity and vice versa. That is, for insulators, they have scarcity of free charge carriers. So the number density of electrons in the case of insulators is very less. So resistivity of insulators is very high. Understood now, students? So definitely resistivity depends upon the nature of material of the substance, right? Whether it is a conductor, it is an insulator, accordingly it will offer large resistivity or small resistivity depending upon the number density of electrons. So that's the first point. Second, which is very important, for a given material, rho is inversely proportional to tau. This is very important. We need to understand this concept, the theoretical interpretation. Now look, students, we are already aware resistance theoretically means that the hindrance, obstruction or the opposition offered by the vibrating ions towards the movement of free electrons. Now consider the temperature of the conductor is raised. So the conductor will gain in kinetic energy, isn't it? So the positive ion earlier, which was vibrating like this, now with the increase in the temperature it will start vibrating with greater amplitude and more vigorously. Again I repeat, with the increase in the temperature there will be increase in thermal energy. So as a result, the positive ions of the conductor starts vibrating more vigorously and with greater amplitude. Earlier if it was oscillating like this at low temperature, now at high temperature it will start oscillating more vigorously and with greater amplitude. So students, look, when the electrons are drifting in a particular direction, then they very often collide against each other, that we are aware. They also tend to collide with the vibrating ions. Now since these positive vibrating ions vibrates about the mean position with greater amplitude and just more vigorously, therefore the probability of electrons colliding with the vibrating ions increases. That is, the collision of electrons with the vibrating ion increases. The probability increases. Collision takes place much more frequently. Now when collision takes place much more frequently, then the time between successive collisions obviously decreases. That is, the relaxation time decreases. So students, what we have concluded is, with the increase in the temperature of the conductor, the collision of electron with the vibrating ion, its frequency increases. Therefore, the time between the successive collision decreases. That is, the relaxation time decreases. So, what's the conclusion? With increase in temperature, average relaxation time decreases. Right? Now, with the decrease in the average relaxation time, the resistivity increases, and therefore resistance also increases with increase in the temperature. So this is the conclusion basically, students. Again I repeat, with the increase in the temperature, temperature of the conductor, the positive ion starts vibrating more vigorously and with greater amplitude. So the probability of an electron colliding with the vibrating ion also increases. That is, the collision takes place much more frequently. That is, the time that has elapsed between successive collision decreases, or in other words, relaxation time decreases with the increase in the temperature. With the decrease in the average relaxation time, the resistivity increases. So what's the ultimate conclusion? The resistivity of the material of a substance increases with the increase in the temperature. Now if resistivity increases, then resistance will also increase. So how the resistivity or resistance depends on temperature. With the increase in the temperature, the resistance or resistivity of a conductor also increases. So what will be the reverse effect of this? If the temperature of a conductor is decreased, the resistance or resistivity of that conductor will also keep on decreasing. And students, this concept forms the basis of superconductivity. That also we'll discuss in some later section. Right? At a very low temperature, the resistivity and hence resistance of a conductor disappears. It is only then that the conductor is said to have become a superconductor. Anyway, we'll discuss that later on. But for the time being, what we have derived is very important. Mark my words. The resistance and hence the resistivity of a conductor increases with the increase in the temperature and decreases with the decrease in the temperature. Right? Okay, continuing with this topic, let's concentrate on the other one, that is the temperature coefficient. It is related to same concept only, the dependence of resistance or resistivity with the temperature. So what we consider is, in order to consider on this particular term, what we consider is, let us consider a resistor offering resistance R0 at 0 degrees Celsius. Now just now we have discussed, if we tend to increase the temperature, the resistance of this given conductor will also increase. Just now we have discussed, right? Suppose the temperature is increased and at theta degree Celsius, the resistance increases to R, right? So students, what is the increase in the resistance of the conductor? It is R minus R0. This is the increase in the resistance of the conductor. This increase in the resistance of the conductor is found to be dependent on the resistance of the conductor at 0 degrees Celsius. The original resistance of the conductor at 0 degrees Celsius. Also, this increase in the resistance is found to be proportional to the temperature difference. Here the temperature is 0, final temperature is theta. So temperature difference is final minus initial, that is theta minus 0, that is theta. So we can combine these two. On combining these two, we get R minus R0 is proportional to R0 theta. Now students, we are aware, in order to eliminate this proportionality sign, we need to introduce some constant, right? So R minus R0 is equal to, this is constant, this is alpha. This is the proportionality sign and this is the constant of proportionality, that is alpha. R0 theta. Student, this constant is known as the temperature coefficient of the substance. We'll discuss this only. So, the expression can be R is equal to, after rearranging the terms, R0 1 plus alpha theta. So, this is one of the formula relating R, R0 and alpha with the temperature. This can be used in solving certain numericals based on resistance and a dependence on temperature, right? And alpha, as I stated, it's the constant of proportionality known as the temperature coefficient of the conductor. Let's define it. Alpha may be defined as R minus R0 divided by R0 into theta, right? So how to define it? Student, in case of conductors, when theta is increased, R minus R0 will have positive value because R would be greater than R0. So this will give us the increase in the resistance. So numerator is the change or increase in the resistance. R0 is the original resistance at 0 degrees Celsius. And if we consider theta to be 1, that is for each 1 degree Celsius increase or decrease in the temperature, right? So let's try to define alpha. Please listen to me very carefully. The temperature coefficient of a conductor may be defined as the change in the resistance per unit original resistance at 0 degree Celsius for every 1 degree Celsius rise or fall in the temperature. When I talk about the rise of temperature, then there will be increase in the resistance. When I talk about the fall in the temperature, then there will be decrease in the resistance only in the case of conductors. Right? So I repeat, alpha, which is the temperature coefficient of a conductor, is defined as the change in the resistance per unit original resistance at 0 degree Celsius for every 1 degree Celsius rise or fall in temperature. Right? Now regarding its unit, resistance, numerator it's measured in ohm, this is in ohm will get cancelled, so we'll be left with reciprocal of temperature. So SI unit is per Kelvin. SI unit of temperature coefficient is per Kelvin, right? But normally it is also expressed in per degree Celsius. So these are the units which we use in order to express the temperature coefficient. Now again we need to discuss some special cases. Now look, first one, for conductors, alpha is positive, that is, its value is greater than 0. Students, for conductors we have discussed the resistance increases with the increase in the temperature, right? So, if theta increases, then R would be greater than R naught. And if numerator is positive, then alpha would be also positive. So the value of alpha greater than 0 or the value of alpha is positive. It suggests that in case of such substances, the resistance increases with the increase in the temperature. And that is when we consider the case of conductors. Right? Second, for semiconductors, there is an entire unit of semiconductor in the curriculum of physics in +2. We'll discuss it in detail. But as I told you, semiconductor means semi, neither extreme. Its conductivity or resistivity lies in between that of conductors and insulators. Right? Silicon, germanium, they are the best examples of semiconductors. For semiconductors, alpha is negative. So students try to interpret, or alpha is less than 0. Alpha negative means with the increase in the temperature, R minus R naught is less than 0 or negative. R minus R naught will be negative only when R is less than R naught. Means initial resistance at 0 degree Celsius is greater than the resistance at theta degree Celsius. So what I mean to say is that alpha can be negative only when R is less than R naught. That is, with the increase in temperature, the resistance of such substances must decrease. So, the behavior of conductors and semiconductors, they are exactly opposite towards the temperature. For conductors, alpha is positive, which suggests that the resistance increases with the increase in the temperature. For semiconductors, alpha is negative, which suggests that the resistance of a semiconductor decreases with the increase in the temperature. Right, students? There shouldn't be any sort of confusion. There's another important point. For standard resistance wire, now in electrical measurements we will make use of certain devices like meter bridge, potentiometer. There we make use of standard resistance wire. It's basically made up of alloy, manganese or Constantan, Eureka, right? These are the alloys which are used for making standard resistance wire. So for standard resistance wire like made up of manganese, Constantan, Eureka, the value of alpha is very small. Now we have discussed the value of alpha positive, the value of alpha to be negative. Now we need to interpret what it suggests when the value of alpha is small. Not positive, not negative, it is small in magnitude. So what does it suggest if the value of alpha is very small? If the value of alpha is very small, it means that R minus R naught is very small. So the change in resistance with the change in the temperature is negligible. Students, when we make use of our resistance wire, our intention would be, or the preferable situation would be that the resistance value of the given wire doesn't change with the change in the temperature, isn't it? So for that, we choose that material having low value of alpha. Low value of alpha suggests that the variation of resistance of such materials with the variation in temperature is almost negligible. It can be avoided or neglected. So when we make use of standard resistance wire made up of constant or manganese, then first it offers very high value of resistivity, which is the foremost condition for a wire to be a standard resistance wire. And second, it possesses very low value of alpha. Very low value of alpha suggests that even with the change in the temperature, the resistance of such wires will more or less remain same. So, this question is important from Viva point of view as well. What are the properties associated with a standard resistance wire? And standard resistance wire is made up of which material? So students, once again I repeat, in order to make standard resistance wire, we make use of alloy, constant manganese, or eureka. It is known as eureka as well. And what are the properties which it must possess? First, a standard resistance wire must possess high value of resistivity, because it's used as a resistance wire, so it needs to possess high value of resistivity. And second, which is very important, it should possess low value of temperature coefficient, which will suggest that even with the change, increase or decrease in the temperature, the resistance of that particular material of the substance will more or less remain same. So students, today we have discussed very important topic. I hope you have understood it completely. Please go through this topic thoroughly and always watch my video till the very end. Right? So next time we'll continue with the other topics as well. Till then, do take very good care of yourself.